Okay, this hacking session is about discussing, sorry for being late. It's an hacking session, so it's a discussion after the presentation we had yesterday about predicting the next event on the system. And while we were doing implementing this solution, we were facing some issues with the measurements. The first one was the exit latencies. So we saw with the exit latencies, we saw when we want to do statistics, we measure intervals. So the current approach is to measure the duration between the moment when we enter idle and the moment when we exit idle. The point of the measurement is the get local clock, and that can happen only when the CPU fully wake up from the sleep state. That means there is a latency between the real moment when the event happen on the system and the moment when we can measure this value. So we have the characteristic of the exit latencies. Yeah. So we have the characteristic of the idle state with the exit latencies. This exit latency is not constant, and that's especially true when we have a cluster idle state. That means the first CPU waking up will have an exit latency which is higher than the other CPU, and expecting if the other CPU are not waking up at the same time, that those waiting for the first CPU to finish the accomplishment of the task of waking up the cluster. So that means we have a variable exit latency, and this exit latency is not negligible. It has a significant impact in the measurement because it can be up to 2 or 3 milliseconds. So it's a lot because it's almost the size of the target residency. That means when we measure the sleep duration, we measure also the exit latency with the sleep duration. And when we try to do prediction on the next sleep duration, we take into account this exit latency. And then we think we can go in deep idle states, but we can't actually, because we just assume the sleep duration in addition with the wake-up latency. So I don't know if one of you took into account this kind of change in the exit latency. Now, in the computation, we retrieve the exit latency when we have the sleep duration, but with the cluster state, this exit latency, depending on the OBP, depending on the fact that it's the first CPU exiting the cluster state or not, there can be a very big difference. So I had the idea to implement dynamic exit latencies. So at runtime, we try to change, depending on the state of the cluster, we change the exit latency.
Yeah, but what will be the performance impact on that? I mean, you mean that when a CPU wake up, you want to notify the other CPU that their wake-up latency will be shorter because they will not be the first anymore?
Yeah, but that's too late at this moment, because if the other took the decision to go to the cluster state, they already choose the idle state. But when we exit, when we have what we want is to be as much accurate as possible when we measure the sleep duration. So when we exit the cluster state, we know that we are the first one exiting the cluster state. So we know that the exit latency is higher. So we can subtract from the sleep duration this exit latency. And the other CPU waking up, which is not, if it's not the first one exiting the cluster state, we know that the exit latency in this case is shorter. So we can retrieve this exit latency from the sleep duration.
And my point is that for that, it means that you will have a shared
Yes.
across CPUs.
Yes. I think it's, if we do best efforts, it should be just based on skate domains, and let the skate domains tell, okay, all domain is idle, something like that.
So the skate domain of per CPU?
There isn't a parent skate domain for the cluster?
No, but the skate domain, what we call skate domain in the scheduler, it's the structure as per CPU. It's not shared at the first seat.
Yeah.
I mean, if you set a value in the skate domain of CPU 0, this stays CPU 0. Then what you want is a shared structure between all the CPU. So that when a CPU update that, the other CPU in the skate in the same level will see this new value. That's what you want.
Yes.
So it's not skate domain.
Okay.
That there is other, and the other point is that this is a critical section, which means that so what you're proposing should work for small system like mobile phone. What about server side? When you have 128 core.
But can we have cluster for 100 states? Can have eight, I think. 8. Oh.
I think most of the big ones actually have very small clusters. You typically have a lot of clusters with only 2 or 4 CPUs.
Yes.
So you could have 8 CPUs in a cluster, but as far as I can tell, most of the big systems have much smaller clusters.
Okay. So they are trying to make disappear the cluster thing, just being in the CPU basis?
I think it's mainly because of caching characteristics. Okay. You want it gets better if you make the clusters a little smaller, but not just one CPU. You could also have clusters of just one CPU, but for some reason you don't get that either.
Okay.
So it's the most of them that I see have 2 or 4.
Okay.
I guess there is these nested clusters as well. So you have like a cluster and a cluster above it.
Oh.
I mean, from an idle state point of view, at least. Yeah.
Okay.
That's probably not what. That's not for mobile phone. I agree with you. I should probably have 1 or 2 clusters, maybe not more. With 8 CPU.
Yeah.
But that also means that what you are proposing should probably work for mobile. But what about other systems? That's my point.
I have a different worry here, which is I can't tell how strongly correlated the estimate would be when you go to sleep. You know whether you are the only one in the cluster or not, but that doesn't mean that you will be the first one to wake up when the wake up comes. So if you have 2 CPUs in a cluster and they both go to sleep, then one of them will see that there's still another CPU, so it's not the last one. The second one will see that it is the last one, and so they would see different expectations for the wake-up latency. But then there's, in the two CPU example, there might be 0 correlation between who goes to sleep first and who wakes up first. I'm not sure how good you can estimate that.
But you can estimate if you are the first one or not, when you wake up. Because what is interesting is you measure the idle duration. So when you exit, what you are interested in is the point where you are effectively wake up, when you receive the event. And the point, there is a gap between the point when you are wake up, woken up, and the point where you can measure. So where the CPU can operate instruction to do the local clock. So this gap is shorter. If you are the first one, you know that this exit latency is is higher because you are in a cluster state and you know you are the first one.
Right, but where does the information come from that lets you know whether you will be the first one to wake up or not? Because you don't have an estimate of whether the other CPU is going to be at sleep by the time when you wake up. You can guess when you will wake up, but I don't think we have a mechanism for guessing whether the other CPU will be asleep or running at the time.
You want to use a ref count? Something
Yeah,
like that?
I think it's we need a ref count, something like that.
The problem is what you're saying is that the first one will take more time to wake up, but
Yeah.
we have also seen that when all the CPU are trying to wake up at the same time,
At the same time, yeah.
the first one is the one with the shortest wake-up latency, because the other one has to wait for the first one to wake up, and they will start. Their wake-up will be delayed. So at the end, if you're not, in some case, if you're not the first one, you will have more latency. How will you handle such situation?
I think we cannot handle this situation.
Is that kind of a worst case scenario as well? So it's probably the case that you don't have to care that much about.
Maybe a comment.
Is it?
Why would you wake up two CPUs all the time? There's some things that we do in the kernel where we wake them all up. So there might be one CPU running in one cluster that wakes up all the other CPUs to call a function on all of them at the same time. And then if all the other CPUs are asleep at the time, it will wake up every single CPU in the other cluster at the same time.
Right, but I'm just saying that is that like the most common scenario, or it's like quite...
That of course is workload dependent, but it is something we do.
But if it's workload dependent, well, late in the wake-up process, really do it immediately when you wake up the first CPU. The thing here is that we want to find out this exit latency for the first CPU, and we want to do that really, really early, as early as possible in the wake-up process. So when do you wake up these other CPUs? Do you
No,
know?
but you can wake up several. I mean, the point is that you are a task, and you can wake up three other tasks at the same time.
Yeah, but isn't it the scheduler that does that decision? So that means that
No, it's not the scheduler. It's a random kernel function that calls SMP call function with the argument of call every CPU.
But do you do that in the process of wake? Don't you just wake up the first CPU and then you do
Well, this assumes that there's something running on one CPU. So that one CPU is not asleep. But you might have two clusters and every CPU in the other cluster is asleep.
Yeah.
So one CPU does something in the kernel that requires calling something on all the other CPUs. Like, yes, it depends on, for an ARMv8 we probably don't need it for invalidation. So on older CPUs we had to do it for TLB invalidation, for example. That would be one thing that we would do quite frequently. When process exits, we might have to.
And even if one thread wants to wake up, let's say, 3 new threads, and even if you do that sequentially, we see that the wake-up latency of a cluster is several milliseconds. But
Yep.
when a thread is running, you don't need several milliseconds to wake up. So it's almost at the same time.
And-
Maybe you will have.
A more common example might actually be user space, where you start up.
But
in
that's fine. I mean, that's way too late. Not too late. That's way late in the process. We've already taken the measurements by then. The problem is not that we wake up all the CPUs in any later stage.
Okay,
It's really.
Yeah, but you will wake up. You will wake up everything at the same time.
that's
So
what I mean.
it's the PCI firmware waking up everything. Is that what you're saying?
No, even if it's at software level, it's really short. I mean, let's say you have CPU 0 running a task, and this task say, okay, I want to wake up 5 new tasks that will do whatever.
Yeah.
Just
You
do a
will
lot of
that
forks.
in 10 microseconds most probably, or let's say in 100 microseconds you will do some task wake up
Yeah.
sequentially.
But the scheduler does that. No.
Yeah, but at that time, I mean, when you will wake up the last CPU, the last thread, the first thread and the first CPU will not be woke up yet, because you need 2 milliseconds and we have just read for 100 microseconds. So you will have to wait.
So that will correlate with the second point of the question I will have, so the task wake up. But I do believe that this situation where we have to wake up all the tasks on the cycle of all the dynamic we have on the CPU that represent a small situation when happening a few times regarding all the rest of the situation. So I think we can live. We live with that.
And there's probably nothing we can do about it either, because it's just a fact that some applications do this, and we have to deal with it. But we can't estimate the.
No. Yeah.
But I still don't see the answer for what I asked earlier, which is how do you figure out whether you will be the next CPU the first CPU to wake up? Because is this correlated to the knowledge of who goes to sleep first or not?
No. No, it's not.
How long? Or sorry, the knowledge of how long you expect to sleep.
No, the goal is that in the wake-up pass, you have a ref count, and you do something like testing. And if you're the first one, you mean that you have done the cluster wake-up.
Right, but what does that tell the others?
That
The others don't.
wake-up latency will be shorter because they will not have to wake up the cluster, but only their core.
But that's. But
And the difference between, at least in the
It's just in the per CPU context, you have to know what latency you have to choose. If you are the first one, if it's a cluster state, if it's a CPU powered on state, you don't care about, okay, about the others. You just know that CPU, there is no dependency on the idle state with other devices, which is the CPUs, and you say, okay, I know my exit latency is constant, is the same value, and I don't have to care about if I am the first one or not. When I am a cluster idle state and you wake up, you have to say, okay, if I am the first one, then my exit latency is this, because you put that in a table. If you are not the first one waking up, okay, the exit latency then is the other exit latency in my table, because I'm not the first one. The only information you need is, am I the first one or not?
yes, but where do you get that information from?
So this information is how do you describe, so that's another aspect of the problem, is how do you describe that? Because today we know that they don't, ARM told us that they don't want us to tie the power domain with the cluster. So usually what we did until today is to take the topology and say, okay, we have a cluster and that's a power domain. But they don't want that. So we need a power domain to describe the cluster. And we need an idle state to be tied with this description saying that this idle state will pour down all this power domain, and in all this power domain we have all these CPUs. And we can put there a ref count saying we have n CPUs on this power domain, and then you just do a test in the wake-up pass. But we need a way to describe that.
You have a flat hierarchy in device with a flat way to describe the CPU idle state.
Yes, but in this case, that means that this solution only applies for platform with device tree and power domains.
Oh yeah, it's only for platform.
So we cannot generalize that for the others. That means we have to do this in a...
I don't see the problem in describing. I mean, that may also be a problem. But the problem that I'm trying to figure out whether it's even possible is, let's assume there's a cluster with 4 CPUs, 3 of them are already asleep. And you know that if you are the first one to wake up, you will have this extra long latency. But by the time you wake up, how do you guess whether the other CPUs are still asleep or whether they will have woken up?
So, in the cluster idling series that I've been working with, we know this, because we need to know the last man, and we also need to know the first man. We also get to know the first man because of that.
Where does the information come from?
So, because of I mean, it's a structure that's been locked. So it's protected data. So you know that in this platform coordinated mode versus the OS initiated mode in the PCI, if you know about how the OS initiated mode works, it's a different way on how you provide the cluster idle states to the PCI firmware. So you actually have to do that on the last man standing. So that means that
what we are doing to solve the problem is that we're using a YEN-PD structure and put CPUs in that as a regular device in the domain. So there is a lock. It's a spin lock where we have to maintain this data.
But where does it come from? How does that loop with the data? Like, you don't know when you have an estimate of when the other CPUs are.
No.
You're doing that at wake up, not when you're not when you're entering the sleep state.
So it's being reference counted within the lock. It's being
make a decision before you go to sleep.
No, at wake up, when you woke up, you increase the ref count. If you were the first one, you know the latency. If it was already increased by another one, you can select another latency value.
Well, when you wake up, you know what latency could have been. Yes, right.
Yeah.
But
No, when you wake up, you can know if you're the first or not the first one.
yes,
In the process.
There is
By that, you can select between two values.
in the firmware, the PSCI, when you have the first one, the other CPU will be blocked. So if all the CPU wakes up more or less at the same time, the first one has to do a list of operation,
yes,
and the other will be blocked. Done. So when you exit the state and you do best effort. I mean, we don't have to have something perfectly synchronized. We try to do we don't want to take lock, and I think if we have a ref counting, it's enough. Maybe I misunderstood what you.
I think we're completely missing each other.
Okay.
What I mean is, the only time when you need to know the exit latency is when you go to sleep, right?
No.
No?
When you wake up, what you want is measure the idle duration. How long I have been sleeping.
Okay.
Yeah, it's
So-
how long you have been really sleeping, not how long you are going to
Probably
sleep.
want to show your other graph.
That's the point. We are not trying
This
to,
one? Hmm?
predict the sleep duration. We need to get the
Okay.
accurate measurement of our sleep duration. That's the point.
So you see here, you need you have to reach the time, the target residency, in order to reach a break even. Okay. So the interrupt, waking up the logic, is coming here. But you measure when you wake up. You have all the time where you wake up, and then you can measure the time here. So you will be measuring from there to there, instead of measuring from there to there. We
Okay.
need exactly this.
Right, got it. Yes.
So we need to subtract this.
Yes.
This.
No, that's, okay, I know
this.
what I think. Yeah, that's okay.
And because the exit latency are very high on the mobile, it's not neglectable. On the Intel platform, it's some microsecond. And on the platform we have, it could be 1 millisecond, 2 milliseconds, 3 milliseconds to wake up.
Yeah.
So it's a lot. And it's a lot because regarding that, it could be as long as the target residency. So if we measure the entire sleep duration, next time we could have been sleeping just that, so not reach the target residency. But as because of the exit latency, we have this lens.
I understand the point now.
And then we
Good.
go to
Yes,
sleep
yes,
state,
yes.
deep sleep state, thinking that so we have to subtract this. So
Yes.
to be more accurate in the measurement. So that's the idea of creating just maybe have a ref count, and then the first one just
No, it's fine.
so, okay. So this is the description. I think the problem we have is the description of that, because this dynamic exit latency will be more platform will be interested in that, not only us.
Are you sure? Because if you say that for Intel, the wake-up latency is few dozen of microseconds, and it's not a problem.
Yeah, but we have to change the generic framework for that, for exit latency. We have to go to change the structure of the generic framework. So that will impact other.
Yeah, but it's not because you're enabling a feature that the other one have to use it.
No, yeah.
If they don't,
And I'm pretty sure that on x86 you also have widely different as high, but it could be
And
everything just
and
10 times
compared to the
faster, but
residency,
Yeah.
same problem.
So-
that's another thing. For the Intel, you say that the wake up latency is really short.
Yes,
But what about the residency time? Isn't it?
they are short also.
Yeah, so they can face the same problem. I mean, it's not because the wake up latency. is
Yeah,
only
it's the
100
ratio between the exit latency and the.
If the residency time is only 100 microseconds as well,
Mm.
you can face the same problem that this additional wake up latency will move you in the wrong residency.
And they are also
Yeah.
getting deeper into sleep states where they put down, where they put the whole short bridge to sleep and all that.
Mm. Then you did some measurements with the platform, the iKey, and with you, we were able to see that on the exit latency, with depending on the OPP, the change of the exit latency can be significant,
Yeah. Yeah. There was, I don't know.
up to 60%, if I remember correctly,
I don't remember.
from 2.4 or 2.7 to 1.7. So
Yeah, maybe.
Milliseconds?
yeah,
What's it doing in that?
Also, for example, you have to power up and wait PLL to lock. You have to power up a rate. So I think that for the longest, the situation is that you have to power up your voltage regulator. So you have to wait the voltage to increase. Then you have to lock a PLL, and you have to wait for the PLL to lock. Then you can wake up the CPU, and you have to re-enable the coherency
So it's
stuff.
actually the fundamental. It's not that someone did something wrong there.
No.
But doing some I2C communication or something.
Yeah, there is no S2C involved in the past. It's just that,
Okay, it's really the physics behind it that takes up.
yeah, it's looked like that.
yeah. So as we are trying to having some dynamic exit latency, depending on the situation, we shouldn't we also take care of the OPP? So when we wake up, we look at the OPP. What is the OPP? And then we know that we are the first one or the last, or not the first one, and then we are at this OPP, so we have this exit latency. Shall we feel this to be at?
You start to have a matrix of value.
Yeah,
Is it like going back to the original energy model?
But for the OPP, the impact on the latency, there are one issue is that, for example, the CPU 0 into the idle state, but the CPU 1 is in the same clock domain. So CPU 1 will trigger the CPU frequency change. So do you know that for the CPU 0, the first part in the idle state and the second part in the idle state maybe have different.
it could change in the middle.
Yeah,
Yeah,
yes.
I know, but as we are with this concurrency between we cannot handle all the concurrency. So I assume that we have to live with that and accept that this situation when we have all the CPU waking up at the same time or having a CPU changing the clock while we are waking up, we can assume that these are small windows. We can assume that, okay, it's part of the error. But we try to reduce as much as possible the error margin when measuring. That's, yeah.
How many OPP you have a Qualcomm CPU? 20? Yeah, I'm afraid that with 20 OPP, 2 latency if you're the first and not the other one,
Even the clusters have different OPP.
that you will have a huge matrix to handle. Does it worse the effort?
Another idea, which may be completely insane, but the firmware does have the correct time. It knows exactly how long it slept, right?
No.
If you call it
No,
PCI.
even it cannot, no.
But it has much more, like it does have all the knowledge about the hierarchy and
Yes, but he cannot know exactly when you wake up.
no, it doesn't. Doesn't? Why not?
No, because it's between, it's the logic. The logic is waking up, and then the firmware as well as the kernel has to operate after.
The firmware can only know when the firmware first gets started. That does some things, but okay. Yeah.
Maybe you can, you have this clock event which are resetted when you power down the cluster. Your local clock, you have this local timer. When you power down, so it starts at reset. So if you're able to enable it automatically when you wake up, you can count the number of cycles. If you have a way to count the number of cycles since the CPU power up, maybe this can be done automatically, and in this case you are safe. You just have to read the counter, and you will know how many cycles you have since the power up of your CPU. That could be another way, maybe that would be far more easier for you to handle. So you will have the exact value,
Okay.
but we need to, I don't have enough detail to know
Is-
if it's possible.
Is it something could be a generic for all the platforms? Not Intel, I mean, but for ARM, for example?
This has to be, maybe we should discuss with some SOC manufacturer to know that.
Okay.
In principle, you have to go and ask the PCI firmware, give me this number of cycles since you.
No, because, for example, for this local timer, you have the secure and non-secure register which are available.
Ah, okay.
So we are already using them.
Okay.
But the timer count is not connect with the CPU frequency. So why you don't use why not use the performance unit counter?
Yeah, but that can be also the performance of the PMU can be used, because normally the clock counter of the PMU is stalled when the your CPU is off. So you will know exactly how many cycles run.
Since the real wake up. Oh, okay. So that could be.
Here, because I think they did those experiments, and
Okay.
it's very expensive.
Yeah, the problem is that the PMU counter are expensive, but I saw that there was some new counter which start to be available, which are far less expensive.
I think the PMU counter may be much less latency than the external timer counter, because the external timer counter, for example, use the APD bus, right?
Yeah.
But for the
And yeah,
PMU counter,
yeah, you are using this local bus.
yeah.
Yeah.
Is that something can be implemented in prototype easily? Or it's
I don't know what
Just-
you mean by easily. I mean, by
Prototyping.
the sequence, maybe
no,
not.
no. What I mean is it something we can answer? Can we answer the question? Is a suitable solution,
I think
more or less easily, or it's that implies a lot of development? Or
using the PMU, I think that could be quite easy to
Okay.
do a hack on that.
That's the only generic thing you have. Everything else would be platform specific.
Yeah, but then
Okay.
you can provide a framework to get, because it's just about reading a counter and to value. So when you enter sleep state, you can read the value of the counter. And
Yeah.
when you wake up, you read this value.
yeah.
And because the counter is stalled between the idle state,
Uh-huh.
you know exactly how many cycles.
Okay.
And then, if you know at which frequency you are running, you should be able to get the duration. Do you know the frequency?
Okay. Maybe I will ask you some information about that. I got a PMU. It's not my. It's not my domain.
That
I
would
mean,
be
the
far
architecture
easier than
information.
trying to.
Yeah, I mean, even the performance monitoring unit, I think there's bits that are mandated by the architecture, and then there's bits that SoC vendors can do on their own. So depending on what SoC you're running on, you might have access to better information, but
Yeah.
it's not generic.
Okay.
But that's what I was thinking with doing it in the firmware. If PSCI knows which information is reliable or not, and it can make estimates, then just returning a number of milliseconds, nanoseconds, from the interface that puts it to sleep. By the time you wake up, you could get a number back, so you could have a replacement interface for just instead of going to sleep and coming back, go to sleep and return the number of the nanoseconds you have been asleep.
Yeah, like a select main loop, something like that, with timeouts, you mean? So when you
Yeah.
exit, it tells you if you reach the timeout or how long it's
Right.
remained, something like that.
Just change the add a new firmware interface that does the same thing as before, but returns a number.
Okay.
Like PSCI button to
So with ATF you already have some metrics which are available, but the goal normally is to measure their time. I mean, how many times PSCI or ATF used to wake up. Now, I think probably nothing prevents them to also add this hardware sequence. So I would say that in principle some interface might be already there.
Okay, to be investigated. So I have another point. So I would like to discuss is, so we saw that for audio and video, in the test for those who were not in the presentation yesterday, in order to do comparison to see how behave the menu governor, I created others governors to compare with, and one of them is the shallowest. So this governor is just always choosing the WFI in an idle state, and we see that for this scenario, which is audio and video, we consume up to 8% less energy for video, and for audio we consume less, just doing WFI. So that means there's something happening here. And when we do, we look at the canal traces with WFI and with the menu governor, we see that with the WFI, the tasks are packed together, while on the menu governor, well, of course, there is a lot of misprediction because of the task ordering and the dependency between the tasks. There are a lot of misprediction, but when we use the WFI, all the tasks are packed together. So when we are looking for a decision, when we want to take a decision about the idle state, how can we characterize this situation and take the WFI instead of trying to predict something?
Is that a result of the changes to the scheduler where we basically pick the idle, the shallowest state for CPU to wake up?
Just a reminder, I think then you should
Did we make changes where we introduced this? I think Nico.
Oh, yeah, no, I think that there is two things. The first thing is that the menu, we have looked at in detail. And in the case of the menu governor, what we are seeing is that because everything is packed, so it's asynchronous wake up triggered by the scheduler. So when you wake up a task, you put that on the CPU, which is idle, whatever the state.
The shallowest idle, right?
Yeah, but even that, all the other CPU were, as you can see, all the CPU were in deep sea state. So the first task wake up, then it starts to wake up other task. So you will have to wake up from the cluster state. But then, if you don't have anything to do because there is no timer, no IRQ, you will select the cluster power off state. But in fact, you will wake up in few microseconds because you will be wake up back by the other task. I mean, you have this pipeline of thread which happening. So the task wake up another task, you go to sleep. Because there is nothing running on the CPU, you select the cluster. But shortly after that, the other task has finished. So wake up back the CPU, the task.
You break the target residency?
So,
But I didn't get the point of why do we end up with task packing in the WFI?
no, it's just the wake up latency that you see in the between. It's just an effect. You need 2 milliseconds to wake up from cluster. So it's just the wake up latency that you can see between.
And because of this latency between the task, also the menu governor is doing misprediction and taking deepest idle state and so on. So, and the result is when you choose WFI and see that we have 8%, but the governor does not make any difference between the big and the little cluster. So when you have this CPU, it's in WFI. So that means the WFI is for all the CPU. So even in this scenario, we can save more energy, because if we had the second cluster in cluster power down, because it's not used, then, yeah, so by doing that, we are doing WFI for all the CPU, we save 8% of energy. If we have this, let's imagine that this task, the EIS, because here there is a misplacement of the task with the EIS, so this task shouldn't be here. They should be in the little cluster. And all the big clusters should be powered down. So that means that we can have a better, potentially a better energy saving. So,
just to add one thing here is, you've been running this on a HiKey 960.
HiKey 960, yes,
So
big little.
I think it would be interesting to run this kind of test on a x86 platform as well, to see if you get that kind of, what behavior do you get in that?
Yeah, but the problem is you cannot measure anything.
Okay.
Because all you have energy counters on the Intel platform, but all the firmware is overriding the decision you made. So I already tried that. So it's you can see this, but from the energy point of view, you won't see the difference because the firmware is doing something. I think you wanted to say something?
Just want to remind that there have assumption that this use the ES, so the wake-up path is not use the midnight color, the scheduler, the wake-up path to choose.
So I did the same test by disabling the ES in the kernel and disabling a cluster. So running just in a single cluster without the ES, and I have the same behavior.
Oh.
So it's not involved. In this scenario, the ES has a little impact, I believe.
Do you know if there's, I mean, the menu governor does some computation to find out the next prediction.
Yeah.
And in this shallow governor thing, there is no prediction at all.
No.
So it's a lot faster. So how much is that affecting this behavior?
You mean the prediction? The
Yes.
time to predict?
Yes.
It's for more or less 14 microseconds.
So that differs for every CPU when you take the decisions.
Yeah, but I don't think it is significant. I don't think it's significant, and maybe there is, but at the first glance, what I tested, is not significant. I think the problem is the misprediction here. We are badly predicting here, and then we are going always in deep idle state, and we break the target residency because the menu governor is not is doing a soup with all these wake-up sources. It's not able to identify. Now with the new governor we are writing based on the RQ next prediction, we clearly identify the sources, and the need riscade is one of these sources we can discard if it's being very erratic. My expectation is how can we detect that we have a lot of tasks interacting together, syncing together. So in this case, with the multimedia workload is spawning a lot of threads, and these threads are just syncing together. So they are doing a task, and then they finish the task that release the other task in the pipeline, doing the next process, which is etc. etc. And but by cascade, all these tasks are tied together. And Vincent, I remember you talk about a sync thing in the scheduler.
Yeah, you have a sync parameter. When you are able, when you wake up a task, you're aware to say that it's a sync wake up, so that you're waking up a task and you will yourself shortly sleep. So, but because it's, I mean, when you wake up something, you're still running when the other thing is waking up. So if you're looking for an idle CPU, you will not stay on the same CPU because it's already busy. And there is a way to say, I'm going to sleep shortly, so my CPU will be idle. So you can stay on the CPU if you want. But it's not really well used. I mean, it's mean that all the user space stuff and so on must take advantage of this. And it's quite difficult.
Okay.
But this, normally it's possible. Not well used, but possible.
Okay.
What about that new governor, TEO? I mean, is that also mispredicting?
Yeah. It's just ignoring the need resched. So he's taking the timer and guessing if he wake up before the timer, then he should go take a shallow state. But it's heuristic. There is no control. At the end, the result is it picks much more shallow state. So the side effect is we see more or less the same thing than the shallowest here. But it's just a question because it's taking shallowest state, but randomly. For the Jankbench test, this one, he has something similar as this one. So that means that he can have a lot of performances. He has a better trade-off performance energy than the money governor, but he actually does not have control of what's happening. He just choose idle state. So for Raphael, who implemented that, it's for the server side. So I mean, it's for them. It's okay. This kind of trade-off, they can live with that. They're happy with that.
So I think we should also know that they also have a governor inside the firmware.
And they have a governor inside the firmware in addition, yes.
So that means that they could mitigate the problem at that level, in some way or the other, or some magics.
So that governor can override the decision?
Yeah. Okay, so here for this, any other idea to characterize this situation of threads doing a lot of pipeline and parallel processing?
I think that one main problem when you look at all this is that you should find a way to pack everything. You are using all the CPU without any real good reason.
No, here is the yes thing, and this has already been reported, and they don't want to change that. I don't know why they decide that's the way to do. So, but this I'm interested in. So shall we create some kind of nested or interaction CPU between tasks, saying that I have a task, this task took a lock, the other task is waiting for this lock, then there is
the problem is that they are not really taking some lock in some case. It's not always some lock. You can use some wait queue.
It's lock.
No, it's wait queue. They're just waiting for an event. It's not.
They're waiting for an event, but it's a lock. They are locked by another CPU.
I don't like when you say lock, because there is no lock.
Okay, so let's say it's a wait for completion.
Yeah.
So if we can find that the wait of completion, other CPU are using it, shall we say, okay, there is an interaction, I interaction?
I don't know, to be honest.
You're looking for use cases?
Mm. Because if we know that there is...
Otherwise you put everything in a C group and you say this C group should run on the same CPU and you are doing some cost scheduling. mean, instead of trying to detect, why not just grouping C group? It's a control group to say all these tasks share a property.
So you mean from user space, with Android, we detect the exoplayer thing and we just pack all the tasks on one CPU?
You can easily put all the thread linked to an app or a process in the same C group.
Yeah.
And then you can say, I want all these tasks to run on the same CPU as much as possible.
Why? Sorry, what are we trying to achieve here? I mean, with this experiment?
My understanding that you would like to pack everything on the same.
Yeah. Yeah. So if you see here, they are more or less, they are tied together. When one task finish here, that release the other task which processing something, release something, they are packed.
Yes, but what I'm trying to understand is if you are, why are you trying to create this kind of scenario? I mean, Android has the foreground and background C groups anyways.
Yes.
And doesn't that already do something? What you were asking for in terms of
Except that I'm not sure that some of these threads are not part of the foreground app. That's also another thing.
But if you want to scale this workout, you can't do it on a per app basis. We need to figure out a generic mechanism.
Yeah.
It has to be like, I mean, what Android has a foreground, background, or maybe some other.
Yeah. So maybe having some kind of multimedia C groups when you put all the thread involved in the multimedia pass, and you know that they are most of the time they are sequential. That can be a solution. That's the point.
Yeah, but from the governor point of view, what will be interesting, we have this metric, which is the need resched. Okay?
Yeah.
We measure the need resched duration. Instead of the idle duration, we measure the need resched duration. How long we have been running the idle task. So, being scheduled in and scheduled out. It's an interesting metric. We need that, for example, because if we have a task which is running on a CPU and the other CPU is working on an MMC, for example, reading or whatever, and it wakes up the other task. If we are just basing our the prediction on the timers and interrupt, the other CPU doesn't have any interrupt. So we need to rely on this need resched thing and periodic thing in order to predict the next wake up, because we'll be wake up by the other CPU. It's like the timer broadcast thing. So in the same way that when we have this situation, we should take a decision from the governor. What should we do? WFI or deep idle state or so on. I want to detect there is a situation where all the tasks they have interaction between tasks, and so we don't want to introduce latency when the tasks are tied together. They are working together. We don't want to introduce latency in this case.
Yeah, I mean, taking the multimedia C group idea forward, I mean, you could hack up AOSP to allow applications to register that I'm in multimedia, and that automatically puts them into a special C group.
That could be a solution, but it's not a generic solution for the governor itself.
Yeah.
So you want to find out when this scenario occurs?
Yeah.
And trigger the governor to pick a shallow RFI?
Yes.
That's what's your main goal?
Yes. I don't want to put heuristic in the governor. I want to identify, no, that's happening, this kind of workload is happening, I want to do this.
Yeah, another problem is that in your case of audio playback, this sequence is quite short. I mean, the flip between the two tasks is quite short.
Yeah.
But you can have exactly the same scenario, the same mechanism used for tasks running for several dozen of milliseconds.
Yeah.
And if you only look at the wake-up sequence and the completion, that will be exactly the same scenario. Only the time between each event will be different. And in this case, you don't want to wait in WFI.
I agree. Yeah.
So that's why the main problem is that you will have the same event,
Yeah.
I mean a high-level event, but with different
So yeah, so here we are on the other aspect of the prediction. So we have been working on the next interrupt prediction, which is part. Yeah, I will stop. It's part of the three sources of wake-ups. We have a timer. Timer are predictable, so it's okay. The interrupt prediction, it's the prediction is almost done. And then we have the third source of wake-up is the need resched, the IPR rescheduling. And we have to be, there is nothing there which is periodic, it's random. So we have to characterize what's happening with the need resched, with the rescheduling, in order to say, I want this kind of state or this kind of state. We need that. So it's another part of the investigation in order to totally have control of what's happening in the wake-up path and take the right decision from this point. Okay, so I think we need to think about that.
And the keynote is going to start in a few minutes.
Okay, okay. Thank you. Thank you.